So, what can a visitor from another star system actually tell us about our own galaxy? Well, today, we're going to dive deep into exactly that by looking at the orbital and physical characteristics of a really fascinating interstellar object, 3I/Atlas, which also goes by C/2025 N1 Atlas.
This analysis is brought to you by ORCID, and it's built on the incredible foundational research done by Nohil Kodiyatar and Abhay Shamala.
Okay, and just a quick but really important heads up before we get started. This work is based on the most current observations and data that we have. You know, as with any cutting-edge science, ongoing studies might refine or even revise some of the findings that we're going to talk about today. That's just how science works. So here's a quick look at where we're headed. We'll kick things off with some context, then we'll jump right into the astrometric data and the orbit itself. After that, we'll explore its physical properties, try to trace back its galactic origin, and then we'll touch on a super important topic, information ethics. And finally, we'll wrap it all up with our conclusions.
All right, let's get right into it with Section 1, the Introduction and Scientific Context.
So how in the world do you even begin to understand an object like this? Well, you start with the data. The foundational dataset collected right after it was discovered back on July 1st, 2025. This analysis pulls together all those different orbital solutions and uses some really powerful statistical methods to paint the clearest picture possible of this thing's physical traits.
Okay, so let's move on to Section 2 and see how all of this was built. We're talking astrometric data and orbit.
You know, what's truly mind-boggling here is just the sheer volume of data they were able to collect. The observation arc spanned 112 days, and in that time, they gathered about 600 positions from nearly 100 different observatories. And to make sure it was all super accurate, they ran this really rigorous process to weed out any outlier data points. That left them with about 550 high-quality positions with an incredible precision of just 0.22 arcseconds. That's just amazing.
And this table just illustrates the results beautifully. Now, the real takeaways here are the negative semi-major axis and that incredibly high eccentricity of over 6. Both of those are absolute dead giveaways that this object is on a hyperbolic trajectory. In plain English, that means it's just passing through our solar system. It's not captured by our sun's gravity. It also has a retrograde orbit, meaning it's going backwards compared to the planets, and it's moving at a blistering 58 kilometers per second.
So, the million-dollar question is, where did it come from? By basically running the clock backwards on its orbit, we can find its barycentric entrance asymptote. This gives us an incoming velocity of 58.1 kilometers per second from a direction just 11 degrees away from the galactic center. This is huge because it confirms it's not coming from the same stream of space as our first interstellar visitor, Oumuamua.
All right, next up, let's explore Section 3, the physical and thermal properties of 3I/Atlas. This is where we get into what it's actually made of.
This table here shows us what are called the non-gravitational parameters. You can think of these as all the subtle little pushes and pulls on the object that aren't caused by gravity. We're talking about things like gases escaping from its surface as it gets heated by the sun. As you can see, the A1, or the radial component, is by far the strongest force, pushing it directly away from the sun. The fact that the A1 parameter is so dominant tells us a lot. It strongly suggests what we call radioprimacy, which lines up perfectly with models of jets erupting from volatile materials right on the sun-facing side. This moderate activity is actually pretty normal for a comet, and it stands in stark contrast to the whole enigma of Oumuamua's weird acceleration. It's totally consistent with water production rates we'd expect.
Okay, so the thermal modeling uses what's called a fast rotator model. This helps estimate its surface temperature at about 100 Kelvin when it's still far out. But here's the kicker. The analysis suggests it's shedding about 10 to the power of 26 water molecules every single second when it gets close to the sun. That is a huge amount of outgassing, and it confirms this is a very active comet-like object.
So it's active, but what about its spin? Well, by analyzing its light curve, we find a primary rotation period of a pretty brisk 8.72 hours. And from all this, we can start to estimate its size. A radiometric method suggests a diameter of roughly 1.8 kilometers, and that's assuming a pretty standard dark albedo, or reflectivity, of 0.4. The albedo itself is constrained to be less than 0.08, which, it turns out, is a perfect match for the primitive dark D-type objects we see in our own solar system.
Okay, let's zoom out now and broaden our view in Section 4, Galactic Origin and Dynamics.
By comparing its speed and direction to the stars all around us, scientists found something really interesting.
Its motion is a statistical mismatch for our local neighborhood, what we call the thin disk of the galaxy. Instead, its trajectory is a much better fit for stars out in the galaxy's outer arms, giving us a really strong clue about where it might have come from. And this suggests an age somewhere between 500 million and 2 billion years old.
Now for a fascinating and frankly critical topic in Section 5, Information Ethics in Astrometry.
You know, with a discovery this big, how the information gets shared is absolutely critical. So, this research proposes a new standard with 3 key recommendations. First, always show the uncertainty in the data visually, no hiding it. Second, release clear, plain language summaries really quickly, like within 6 hours, to stop misinformation before it starts. And third, require digital signatures from researchers on all submissions to ensure accountability.
And finally, let's wrap it all up with Section 6, Conclusions in Future Work.
So to sum it all up, 3I/Atlas, with its nearly 2-kilometer diameter and that incredible 58 kilometer per second excess speed, really acts as a fascinating bridge. It sits right between the stark, quiet nature of Oumuamua and the really vigorous activity of our second interstellar visitor, 2I/Borisov, and that helps us really hone and improve our models of the entire interstellar object population.
And of course, this kind of work doesn't happen in a vacuum. It builds on previous breakthroughs. That includes the initial discovery by Boland and their team, Jewett's work on understanding the interstellar population as a whole, Michelle's benchmark analysis of Oumuamua's strange acceleration, and even tools developed by Smith's group to fight misinformation. It all connects.
For any of you who want to dive even deeper, we're displaying the full list of references on the screen now. Every single one of these represents another piece of the puzzle, another step forward that helps us understand our place in the cosmos just a little bit better.
You know, as we discover more and more of these interstellar visitors, every single one is going to refine our models and challenge our assumptions. They're literally opening new windows onto this vast, dynamic galaxy that we all call home. It's an incredible time to be watching the skies.